Good afternoon, everybody. It's a pleasure to be here in this talk after 30 hours flying. And I thank for the organizer to be so sharp that exactly this time it was possible. And what I will speak today is a set of issues related with this Shannon mutual information of critical quantum chain. And as I say here, this Shannon is not von Neumann entropy. Shannon, the standard thermodynamic Shannon entropy. And the original part that I will present here that has something was done in collaboration with these people here, Mohamed Hajabpour from Brazil, from Niterói, and Jose Hoyos and John Getelina from the same place I am, São Carlos. Okay. What is it? Okay. Well, I will just give you a very short introduction just to put notations about the shared information in quantum one-dimensional systems in the case of the von Neumann entanglement entropy. And then I will say a little bit, some connections with the two-dimensional Rosard-Kivelson quantum wave function and the relation with the Shannon entropy in one-dimensional quantum chains. And then I will state some universal properties that we believe for the Shannon entropy and also the Shannon mutual information of quantum chains which are conformally invariant, and also that can be integrable or not. We are going to extend the things, and also to discuss something with some model which are not conformally invariant, what this conjecture becomes. And then I close with some conclusion and open questions. Okay. In one-dimensional quantum systems, just to set up a notation, if you consider a system of system C containing capital L sites, I split in two parts. One part, a small l that sometimes I call X, and the rest of the system B. So the von Neumann entropy, in order to calculate that, for example, for a pure state like this one, we just make the partial trace over the Hilbert space of one of the subsystem, and we define what is reduced to the transfer matrix, and then we just compute this trace. This is just the von Neumann entanglement entropy. Now, in the case where we have large systems and also large subsystem size, and we expect two types of behavior. If the system, the quantum chain here is not critical, is a gap, has a gap, then we expect that as a function of the subsystem size becomes a constant. And this, what we say, this is just satisfy the area law, because the area among these two subsystems is just a point. That's the reason. Now, if, on the other hand, your system is critical, has no gap, then what happens is that the system, in this case, the system has this behavior here. There is this violation of this area law with the log behavior with a certain constant here. And what happens is that in the case where the system is conform invariant, this constant here is related to the central charge, which is C over 6, depends on the number of the boundary of your system, or C over 3. Okay, these results here has some time ago, and the finite size scaling versions of these things becomes derived by Calabrese-Riccardi and depends on this object here, which is the chord distance. The finite size scaling function is this object here, which is interesting, as we are going to see. Now, in the case of two-dimensional wave functions, so what we are going to consider as a set of Hilbert space that we can define in terms of localized objects, if you want to say so, that define like a grid like that, and you have degrees of freedom object here that specify your Hilbert space. Just for simplicity, suppose you have like variables which are a plus and minus 1. So you can here consider all the possible configuration of this object, and this represents a basis of one wave vector, okay? And in this framework of this Hilbert space, you can define a general type of wave function of this sort. You make a combination of this object, but you put a coefficient here that depends on the values of these variables here. But the coefficient here, when they have this coefficient, a special relation like that, is just an object like that. So what you have essentially is like the Boltzmann weight, the square root of the Boltzmann weight at a temperature beta of a certain classical system with Hamiltonian density H as Sij. And Z is just the partition function. If you do that, if you look, the amplitudes of this wave function are just the Boltzmann weights. So it's a special type of two-dimensional wave function in this framework that are constructed like that, okay? And you can consider at will this H, okay? And now suppose you do the question, okay, I pick up this general wave function, consider the density matrix of pure states of this type of objects. If you do so, and now you asked for the entanglement of a line just of small L sides in this two-dimensional surface of this two-dimensional wave function, okay? If you do that, so you have the system C, A, B here, and then to do that you have to construct, and I want to compute this, the von Neumann entanglement entropy, then you have to consider the reduced density matrix. In order to do that, I have to sum over all the amplitudes, a square of what I said here, all the places here, and then what we have is just this expression that you are very familiar from the statistical mechanics. This you can write as the trace. If you pick up this and put in a cylinder in this direction, it's just a trace of some sort of transfer matrix that I write exponential minus beta h, or a quantum chain, okay, here at the power m minus 1. The distance, there is m here and m on this side. Here is 2m actually. So what is interesting here is that this is related to somehow this quantum chain here, which governs the time evolution in the statistical mechanics, you say so, among this one line and another one. Now,
where enters the cut? Where you are cutting the two segments?
That's yeah. Here, actually, the trace here is not only the trace over the trace, because at the end you identify this point with this point. When I do this sum here, it's like a matrix product that I go up to here, and a matrix product I do up to here. And still there is a lot of things here because you still have the degrees of freedom of A here. Okay? Let's go to the next steps, maybe it become clear. And then what happens is that if this direction here, M, is very large, this matrix product that I did here before, this product here that go online, will be dominated by the smallest eigenvalue of age, or the largest of exponential age. So this dominates. So at the end, after this product, before doing this summation over the rest of the system B, that I said that, okay, the rest of the system B here, before doing that, what I have essentially is just the wave function of this Hamiltonian, okay, which I split in two parts. I write in terms of two subspace here, if you write like that. And so actually what I have essentially here is just the ground state of a quantum chain. And now if I want just the reduced transfer matrix of subsystem A, then I have to make a trace over B like that. And what I get is just those amplitudes, those objects here that I write like that. And my density, the reduced density matrix, which gives me the entanglement, the von Neumann entanglement entropy of this line with the rest of the system, will be just, I produce this reduced density matrix, will be just this object, and this means what I have here is just the Shannon entropy of a reduced system, a classical thing of a quantum of my Hamiltonian here. So it means that the von Neumann entropy of this two-dimensional system becomes just the Shannon entropy of this quantum chain. So
Chico, to work, I guess the original coefficient has to just be positive, right? Because then I would write as an exponential.
Oh yeah.
That's it,
Yeah,
right?
yeah, yeah,
Nothing
yeah,
else.
Yeah. Actually, you can do Okay, I will discuss this more general thing you can do. You see, this construction here is completely general. You can start something, or you can start with a given quantum chain, come back and say what is the two dimensions. I think it's very general. I think there is a lot of things here to understand and beauty. So what I can say is that somehow if you consider 2D classical statistical model, you can define some sort of this Hoxard-Kivelson wave function. This originates in a wave function for dimers, but this idea is general, is there. And it's plausible that if you have a set of critical 2D systems that belongs to the same universality class, okay, we know very well from conformal field that they are ruled by the same conformal field theory, then we would expect the same universal behavior of the Shannon entropy of the quantum chain. But this is a catch, because the Shannon entropy is something that depends on the basis that you use to express the wave function. It's different from the von Neumann entropy. And so somehow each basis of the quantum chain, it will correspond actually correspond to the two-dimension field theory, or CFT, with a certain boundary condition. And we should then, from this analysis, expect some universal behavior if this boundary condition, which relate to the basis I'm choosing the quantum chain, okay, do not destroy the conforming variance of your 2D classical system, or 2D system. And actually, in general grounds, always we know this, at least two spatial boundary conditions, the Dirichlet-Neumann, that does not destroy. So we should expect some universality in these things because of those reasoning. So what we are going to show is the result of some search for universal behavior of this Shannon entropy, and as a consequence, the Shannon mutual information. Just to understand what is Shannon mutual information, suppose now we consider the same chain as before, the system C split in two parts, and now you want the mutual information and also the Shannon entropy is related to measurements that you can do in your system. So if you choose a set of local measures in the subsystem A, like that, you have this value here, and this is in the system B. And then the ground state you can decompose in the subsets corresponding to these observables here, A and B. And you can mount your density matrix. And if you do a measurement in your entire system, it means you measure the observable A and B. What you get set of value with a certain probability, just given by this expectation value here. And as a result of this measure, you can define the Shannon entropy. The Shannon entropy of your system is given by this object. But if, on the other hand, you do a measurement first on the system B, okay, don't do nothing and ask after this measurement what's the probability to get a certain result. What you get, you are going to have the results of your results will appear with certain probabilities, and then you have a reduced Shannon entropy. Okay, and if you do the same thing, now you do the measurement in A, and then do the measurement in B, you have other set of probabilities, you get this entropy. So then if you measure one system, get one information, or measure another system, get information, the difference of the entropy here with this object, you measure you have a decrease of the entropy because you have much more information already there, and this is decrease of the entropy. And if you wanted to define something related with the information, you just put minus sign of that, and this is just the mutual information. Tells you how much you can know about the system A and B if you know A or if you know B separately. Okay, and but the important thing is this is the basis-dependent quantity. Since you are searching something universal, then we have to deal with this problem here. So a conjecture is that the Shannon mutual information in some spatial local basis of quantum critical chains, we have some special universal leading behavior, okay? And this leading behavior that we conjecture will be something like that. You have just the same thing as the quarter distance, like that, with the central charge in the case of conform invariant quantum chains by 4. Okay, and this is our conjecture. Okay, now just to say, if you come back in the case of the entanglement entropy, not Neumann, but entanglement, you can generalize the von Neumann entropy to the Renai entropy, and the formula that you can have that is just object here where you get this object. And this is universal for any basis. And if you pick n equal 2, you just get c equal 4. So in some sense, this conjecture tells you that, okay, you should expect that in some special basis, the mutual information has the leading behavior analogous to the Renai 2, only in this case. That's what conjecture we have here. Gamma is a constant. We do not know if you have in general, the total gamma is not universal, but if they have some content on it, we do not know. We are still...
I mean, as far as I remember, topological stuff, this is related to the quantum dimension, right?
Yeah, in the case of the von Neumann entropy, but here we don't know. Okay, where this conjecture was confirmed? We are already almost a couple of years in this problem, and there is a lot of, we investigated this in several systems, and what we have essentially, we have tested these things for the Q-POTS model 2, 3, 4, where you know the central charge is 1/2, 4, 5, 1, and we get the numbers, the expected numbers, the numbers we get is relatively close to that, related, and the sites that we have tested is written here. Also here for the XXZ chain, the ferromagnetic, anti-ferromagnetic regime that you have, so the numbers are very close there. Also you can see here also this is for the XXX model. Also the Fatiev-Zamolodchikov model, that's the spin 1 Fatiev-Zamolodchikov model. It's an interesting model that is one sign is anti-ferromagnetic, the other side is ferromagnetic. And the central charge for one case is 3/2 and the other one is 1. And this object also kept the things, the numbers. Also, we looked for the ZQ parafermionic models, you know. So the generalization of Potts model that corresponds to multi-critical point, and the conform anomaly of this object is something like that. That for Z5, 6, 7, 8 is always bigger than 1, and you get this number. This is the exact numbers, and you get numbers reasonably close to that one. And this S and R is because we look at this in 2 different bases. Okay, here we didn't say, but this is one particular result for the one particular basis. So this was tested a lot of some models, but all those models are exactly integrable. So if you really want to test universality, we have to go out of integrability, because as we know, integrability may give you some miraculous things. So the idea is to go out. How to go out? In these tests, it's very crucial that you know precisely the critical temperature. So if you do not know, so it will be very difficult, because we cannot, mutual information you cannot go using like DMRG. It's not the object you can attack by that, because you change bases all the time there. So you have to be basically with your wave function. So what you do, what I report just now, is a sequence of studies in non-integrable models. And for this, I introduce this model here for the case of Eisen model. This is an interesting model that you have the normal Eisen model here, the parameter lambda, but you have this parameter p here. And if p equals 0, just have the standard Eisen, transverse Eisen model, okay? But this p here is interesting because you can show that this model here is self-dual. Oh, the spectrum has this property here, part of the spectrum, important part of the spectrum is this, for finite chain. So it means that you should expect at lambda 1 a self-dual point, and then if the p equals 0 is critical, it's very plausible that this continues critical at lambda equal 1, so that you know the temperature for a certain values of p. Okay, and this is the result here. And then you put this parameter p, go to 0, 0.5, 1, 1.5, even more important than the normal coupling. And what you get as a function of the, now x becomes, the L become x, And you get just the multiple information, exactly this, with the coefficient giving a number very close to 0.5 again. This is for 30 sites. So you see this universality. This is for the Z basis. I mean, you pick up here and consider your Hamiltonian in the sigma Z basis. Okay? But if you do that in the sigma X basis, okay, again, you get the same type of thing, the coefficient is very close, which tells you that actually we are dealing with something which is really universal, not a feature of integrability. Now we did extra checks. Now we pick up these ZQ models. What is this? It's just a generalization of these models, and that we pick up this matrix is here, SR, which is satisfy this ZQ algebra like that, you know very well. And the coefficients here are just given by that. These are special coefficients. And the reason to pick up that is that if you put P equals 0 here, this model is just the ZQ parafermionic models that gives the Eisen model, 3 states model. In the case Q equal 4 is a special point of the Ashkin-Teller point quantum chain, C1/2. And Q bigger than 5 is just central charge C bigger than 1. And you see here that the same thing, this model here is also self-dual. You can keep the property of duality, which is important for this test. And then we hope that for P bigger than 0, a certain value, it will keep the same universality. Of course, if P goes to infinity, there is some symmetries happens and something may happen. And then what we get is that the Q equal 3 case, that you should expect 0.8, you look at the parameters P here, and you get something close also here. Okay, this is the S basis. The letter size here is just 18. And if I look in the R basis, which is the counterpart of the sigma X basis, the Eisen chain, you get again numbers quite reasonable like that. If you now look even more, in this case of the 4 Potts model, here the 2 bases I put together. As you see, this constant gamma is different that Giuseppe asked. You see it's different here. That's why they are. But nevertheless, they give good numbers in the direction for the conjecture. And you can go out. Now, for Q bigger than 4, there is something interesting here in this model. Because when Q bigger than 4, this parafermionic model is just the starting point, is a multi-critical point that starts a line of critical points. So it's not clear that this self-duality will keep the guy in the same exactly multi-critical point. So it was a surprise that when we look, we get numbers that is well, not very close, but plausible to be the same. You should get this number, you get numbers like that in one basis, R basis, in the other one you get something like that. Okay? And if you go for Z6 also, you can go now. Look, the letter size is not so big, it's 12, 11, okay? But the coefficients now should be around that. You see, at least for P equal, around P equal up to 0.5 or 1, it looks like you are in this region, okay? Here maybe there is already finite size is very, very important here because the lattice is small. And if you look for 7, P equals 7, you get again very nice results compared to that one, and except for this P equal 1 in this S base that become a little bit deviation. And also in Q equal 8, you get, instead of 1.4, you get something like that. So it means, it means that this set of models are nice models if you want, for example, a toy model to go out from this Fatiev homological that you keep multi-criticalities there. And this conjecture seems to really universal for non-integrable model also, as it should. Then we start to look, okay, maybe what happens when you don't have a system that's conform invariant, okay? And well, normally what happens is that in those systems that are critical, you have some sort of effective charge, central charge, which is not really central charge because you do not have a conforming variance. So our conjecture in this case is that whatever you get for the Renai-2 entanglement entropy, you should get for the mutual information. That's our conjecture in some spatial basis. Then what you did, we consider the disorder critical eigenchain. Okay, this is you just put the eigenchain, but now you put an overall coupling. Delta is fixed there, but you put an overall coupling, and this coupling is random. Random and takes value between 0 and a certain scale, 0 omega I. And the distribute here depends on one parameter d. When d is very large, you have a very disordered system. When d goes to 0, you have the clean system. So you consider this problem here, okay? And the physics of this problem is just given by the infinite randomness fixed points, a very well understood problem here. And the Renai entanglement entropy for this problem was calculated by many people, Raphael and Moore here, for example, and they get just this factor here, 1/3. This C effective is just log 2, is linked to the what is it? Forgot the word. And what is interesting, this is for all n. For all n, okay? So this does not depend on n, like happens in the clean system, okay? But if you look finite size scaling function of that, you see that actually this x here is not just the chord, it's just the chord length, something more complicated, okay? It's not the chord length. This is a result some time ago with Fagotti, Calabrese, more. But we can do an analytical calculation in this case here because you can use the normalization group here. And what you have is that the mutual information in this case is exactly equal to the Renai entropy, exactly this. So it means that the conjecture is okay in a trivial way because they are exact, okay, the same, all the same. Now then we look a different model. This is an interesting model that now the disorder of your system is not completely. We put only the odd couplings in the odd sides random as before, and the even sides are just equal to the left side coupling. So it's some of what we call a correlated disorder system. Okay, what happened here is interesting here is that although this system is not conforming variant anymore, okay, it shows a very similar behavior as the conforming variant ones. For example, we have very, very precise results that shows that the Shannon entropy of this object is like the central charge, effective central charge, with this factor that you don't have in the other system, times just the simple chord length, the logarithm of simple chord length. And this object here depends on the disorder parameter. Okay, just to have a flavor of how this, look at this here. This is the numerical test that you see for large letters here, for the several mutuals here. Here you divide by this factor so that they should always give you the same thing. And you see very clearly that this proposition here. Now X is the OL. Okay, this result, all of them was calculated in sigma z basis. Okay.
In the case of random, does it make any sense to use a replica or something like that to see an equivalent homogeneous system?
No. The replica trick does not work for this system. But this, in the case, this system is very well known by this Dasma Gupta normalization group. Is one of things that you can do very simply, and you don't need to go to, okay. Because the ground state of this problem is just a set of singlets. That's the basic thing. This log of 2 is because of the singlets. That's what the word I forgot. Now, what we did is that we pick up this model here. Now we put in the x-axis here another parameter here. And here I show you several curves here. Sometimes this E here is just the Shannon entropy, okay? And I divide by n, and then the mutual information where I put n equal 2 here and you see all of them going reasonably in the same line. This C here is effective central child, I forgot to put there. So what you have essentially, it shows this type of behavior, which means that probably this is more deep than just conform invariance. It's something more that you have. This is a very interesting system that I would like very much. The fact that it's very close, the result that you have, what you have conform invariant system, but nevertheless the system is not conform invariant. So this brings several questions.
Yeah, so this factor 1 plus 1 over n, normally, as Giuseppe was saying, I think it comes from replica, no?
Normally,
so essentially, you could think to get this.
Yeah, normally when you have a field theory, you have a conformal field theory, you do it, then you get that. But here, you have a system that you cannot do that.
But why you cannot?
At least, well, because you have random.
No, but you treated the random exactly through replica. Replica trick, I mean, not replica of the rainy.
But then you have to introduce first of all a field theory with this random operator and then do the replica. That's what you say. I don't know. It looks like you have something very, some field theory things.
You convert something which is homogeneous, something which has all the basic symmetry. The only thing you translate the problem in some internal space, and then you have to take some limits.
Maybe, Giuseppe, I don't know, maybe. Because something you have here, because this is too much.
Yeah.
Okay? This is too much. What I know is that the other problem, you cannot do that. Here, I don't know, the field theory treatment, because this, what happened, the physics of this problem here, different from the random singlet, is the physics where the random mass is cancelled. This correlated hopping cancels the random mass. Maybe you can have then a field theory prescription, and then you do replica tracking and get something like that. Maybe. This is something, possibility. I don't know. Now, this is one point here. Is the problem of finite size correction. How should we believe these numbers? Is really the central charge, or maybe central charge multiplied by pi divided by 3.14? I don't know. Well, our number, we are always a small letter size. And this is a tricky problem that break our hand, I would say, our head. And essentially, what happens, in order to build up the boot information, you have to consider the Shannon entropy. And what you have, the Shannon entropy, really it grows, has the most important point, grows with the subsystem size like that. And this is a term that will be important for the boot information, because when you do this combination, you cancel this and becomes this guy here, that becomes beta over 4. So the question is, what are the corrections come here? Because if you want to really to have an estimate to say, okay, is this central charge, whatever, you need to know the corrections. If you give me a set of numbers and you do not know the nature of your corrections, sorry, you made a lot of, you do not know exactly what you have. So this is a problem. And in fact, this problem was raised by Stefan. And Stefan did the following. He picked up just the Eisen model, explored the free fermion relations, and was able to compute the Shannon entropy up to letter size 40. And when he put this type of corrections up to 5 terms like that, x here is the size of the subsystem, and he get a number very stable, beta 0.48, not 0.5, with 5 terms. But if you pick up his numbers, and if you put now log of x over x with a constant, what you get the number very close to 0.5. So it's tricky to know if it really is this or not. So there is a recent study of my collaborator with a student, Ajadpur, Mohammed, and they did the following one. He picked up just, they considered, because when you compute the boot information, you need to pick up all the configurations and then make the sum. He started to say, okay, let's look some spatial configurations. But one spatial configuration you know very well is the configuration in the case of the Eisen model that we have everything up. And this gives you the empty information probability, which you can extract some from field theory and actually you expect in this quantity this correction. So this configuration is expected, this type of configuration. So then he started, okay, instead of look just that, let's look some configuration that you have some structure that you can grow by L, and so on. And he picked up configurations like that, and look, and all of them he found just, and he computed these things here with letters, with subsystem size, because L you can go to infinite, subsystem size up to 25,000. Then you see very clearly that you have this log behavior there, okay? Also, he picked up some configuration that are not precise that one, but variation on that, and several of them is like that. So it's quite possible that when you add all those configurations, this log of x and x is still present. And if this is the case, indeed, this is C over 4. So this is what we know at the moment. Okay. So how is done analytical calculation, this type of thing? You know, what it can be done, what people did, okay? What they do, essentially, they do first, they go to the Renai extension of the Shannon entropy to build up this Renai mutual information, just the standard extension like that, you do like that. And again, this is a basis-dependent object. So the question is if now with n, if there is a universal behavior for arbitrary n, as you have in the von Neumann Renai entanglement entropy, or at least in some special basis. That's the question. Then, for example, if you pick up the Eisen case like that, okay, this Renai, if you think that among all the configuration is dominated by this configuration with the ferromagnet 1, then for n large, what you have is just, you put here just this probability of this object, and this is just the emptiness formation probability. And you can get that, and use this, this object. And this emptiness formation probability you can access through field theory, conformal field theory. And what this calculation basically, to have an idea, is the following. You have this two-dimensional wave that you can even think in this Roxart-Kivilson function like that here. You have the two-dimensional wave function that brings up this field theory here, okay? And then you have this line where you have the quantum chain, and you fix some, for this empty formation, some L sites here. And when you do that, what happens? This field theory here, when you write, it's written naturally is the sigma z basis representation of it. And then if you are here in the sigma z base and these are fixed, this just corresponds, fix that you have equal possibility to up and down. So this means that you are just free boundary condition here. So the sigma x base corresponds to the two-dimensional field theory with free boundary condition. And if you are in the sigma z base and they are fixed, they are just considered, they are just a fixed boundary condition, which are just the two boundary conditions that you do not destroy the conforming variance of your 2D system here. And then based on CFT calculation, you can show that the Shannon entropy goes like that, exactly like that. And but this is valid only for n large. This is very crucial here. N is very large, okay? And our conjectures say that not for n large, just for 1, you get this object here. So which look, okay, just this object here. And so this is a resume what I just told you. This you can get for n large and this. But when you look on numerics on these things, what you see is that clearly, if you look here, I put this system here and make a fitting of this coefficient here to see what is the coefficient as a function of n. So the normal mutual information, okay, will just be here. That gives something closer to 0.5 here. And this function here, the Cn, what happened has this behavior like that. For n large, goes precisely what we expect here, which is this dashed line. But then there is a deviation very hard. And this is for a certain lattice size. Here there is several lattice sizes, the x base and z bases. And as L grows, clearly this will diverge. So, so this trick to try to access from n infinity to 1 has a problem here in this problem. So somehow the replica trick will not work for this type of thing. This is a problem. So you cannot solve this problem like that. But then what we look at that maybe there is a, because as you see here, this Renai mutual information, he has this funny behavior, you know. This is not a normal thing when you think in the measure of information. And in fact, people in information science know the proper generalization of the Shannon mutual information, and they came from what they call the Renai divergences. And it's done like that. You pick up configuration, you split in two parts like that, and then is this the object that you have to compute, not the standard Renai that we look there. And this object here, this is the probability of the entire thing. This is the probability you get that when you specify just one part, IL, this is the other one, okay? And actually this, when n goes to 1, you get the standard Shannon mutual information as before. And you should get something like that, one object like that with another. And what you get now is that I put the old one like that for some letters, and I put this new one. Look, they are continuous, okay, and always growing function of n. So they have a nice property if you are going to do some n extension to use analytical calculation. So this is the proper quantity to do it. Okay, you see here the z basis and here the x basis. So this, there is no divergence for n equal 1. So if you want to proceed something analytically, you should, this is the right quantity. So just to conclude, we have shown that the Shannon mutual information for critical system, integrable or not, shows some universal finite size scaling if the local bases are special. Okay, we do not, at least some, the ones that we saw it is very clear. It's linked to the Dirichlet von Neumann boundary condition. As we know, critical quantum chains has other boundary conditions which are also conformal invariant. We didn't know, we didn't make progress in this line. We didn't look at it. And more, this universal behavior is linked to the central charge of this. An interesting thing here to compare with the standard, for example, Renai 2, that you get the same result, is that the mutual information somehow is something that is a result of measures. It's not, you don't need to really go to the reduce the transfer matrix, whatever. You just measure. So maybe this might be a quantity that may be more accessible experimentally, although it's not so simple also, okay? But since it's related with measurement, this might be interesting. We show also that this conjecture can be extended in this way, that the behavior and the violation of the area law of the Renai 2 and the entanglement, the mutual information, are the same for systems which are not conform invariant, okay? And also the extensions of the Renai mutual information we have not shown here, but also they show some sort of universal behavior, but they are not equal in one base in another one. They show also something that you can compute. So there is several questions here. First of all, the result in general basis, you don't lose the log behavior, only the coefficient in front. Probably the proper analytical calculation of this system will be possible to say what are these coefficients in general, depends on the basis, okay? These are questions. And well, the analytical calculation of these things, it will be very interesting, and especially using this extension that we present here based in the Renai divergences. And then I close this with a provocative question. Can we understand all the physics of a critical chain just by studying the Shannon information containing the ground state wave function, but in arbitrary basis? So you change the base, look at the information, change the base, look information. Maybe you can do all the physics just looking for one object, but in different bases. Okay. But this is a provocative, and that's it. Thank you for attention.
provocative question. What would be the use to look at try to describe the system by looking at the Shannon?
Well, the use is that, well, basically we know very well that if you go to make a calculation, this mechanical calculate the partition function, and all the eigenlevels or whatever, no? But here you just have the wave function. So if you have one wave function, okay, you can now transform it in several bases, and each time you look in different bases, see the measurements, and then you it may tells you what is the ingredient, since you have a field theory behind you, whatever, tell you what is, that's the idea. It's like if you go to a place to know a woman, for example, and you want, and then you stay with how to have father there.
Or you want bases and
yeah, no, she came one time with one dress, look like that. Another time with another dress, another dress. And by his flavor, whatever, you have a whole idea what will be your wife.
So you want to make some kind of cubism while you see.
Yes, yes.
Oh, can you look at the Viterbius in 2 dimensions, for instance?
No. No. This is a good
Case
question.
in 2 dimensions?
No, no.
You expect something like that?
Well, I expect like that by the equivalence of the Hochschild, because what is behind these things is this idea of this Hochschild wave function somehow. Because Hochschild wave function, when you compute the entanglement of some part, is something which independs on basis. And if it is described by something which is universal, a critical field theory, it will be somehow related with that. But I do not know what it is. The whole field is a lot of open questions that it will be nice to be.
Apparently there is